Good day, students. Today we shall look into the rotational spectroscopy or microwave spectroscopy. This is the spectrum of carbon monoxide, the rotational spectrum of carbon monoxide. In this, we can see that this molecule has shown spectrums in particular frequency. We shall see how they are formed. So, spectroscopy is in the microwave region here. And this spectroscopy studies the rotating molecules. Here in the spectrum, the lines are nearly equally spaced and they vary in intensity. The rotational spectra can be used to determine the bond lengths and bond angles in polyatomic molecules. Now, let us classify molecules based on their nature of rotation. So, a rotating molecule is described by three principal moments of inertia: IA, IB, and IC. So here in the picture we can see a molecule, and that molecule has a rotation axis along three directions. It is three because we normally use the Cartesian coordinate system. So we have rotational axis along the A direction, the B direction, and C direction. And likewise, we have the principal moments of inertia, IA along the A direction, IB along the B direction, and IC along the C direction. Here, always we select these directions and principal moments of inertia in the order where IA will be least, then IB will be greater than IA but less than IC, and IC will be the greatest. That is, IA will be less than IB will be less than IC. So there are four types of molecules based on the principal moments of inertia. The first one is the linear molecules. So in linear molecules, the atoms are arranged in a straight line. Here, IA will be equal to 0 and IB will be equal to IC. One of the examples is the hydrogen chloride molecule. Here we can see that the center of mass is shifted slightly towards the chlorine atom. That is, chlorine is heavier than hydrogen. Hence, center of mass is nearer to the chlorine atom. And at that point, we assume our three axes of rotation and the three principal moments of inertia along those axes: IA, IB, and IC. Other examples are carbon dioxide molecule, HCN molecule, OCS molecule, and C2H2 ethene molecule. Now, if this molecule is rotating about the IA axis, okay, so it is along the bond, the rigid bond, it does not show any change in the dipole, right? There will be no change in the dipole. H will be in the position of the hydrogen atom itself, and chlorine will be in its position itself. It is just rotating along that axis. So since there is no dipole moment change, it will not show a rotational spectrum. But if this molecule is rotating along IB or IC, the hydrogen molecules and chlorine molecules, it will continuously or periodically vary its position. And that will produce a dipole moment change, and that will produce a rotational spectrum. Now, the next type of molecules are the spherical top molecules. Here, all the principal moments of inertia are equal. That is, IA equals IB equals IC. The examples are CH4 molecule, SF6 molecule, and CCl4 molecule. That is methane, sulfur hexafluoride, and carbon tetrachloride. If we look into these molecules, we can see that all of these molecules are similar if we view it from any axis. It will all look the same if we look from any direction. And hence, even if this molecule is rotating, we don't observe any dipole moment change. Hence, they do not give rotational spectrum. Now, the next type of molecules are the symmetric top molecules. Here, the principal moments of inertia are related as IA is not equal to 0, whereas IB is equal to IC. One of the examples is the CH3Cl molecule. Here, we have the carbon atom and the hydrogen atoms are attached to the carbon atom. It is located on this side, on the left side. Hence, this is the positive center of the molecule. Whereas chlorine being a heavier molecule, it is associated here on the right side a bit more further from the carbon atom. Hence, this side, the right side, is the negative center of the dipole. Now, when this axis is rotating along this bond length, HCCl bond, it does have a moment of inertia because there is a distance r towards the hydrogen molecule on either side. Hence, IA will be equal to m into r square. So that is why IA is not 0. Now, we have the center of mass which slightly shifted towards the chlorine atom since it is heavier, and the three axes along with the which the principal moments of inertia are associated are shown. So the molecule can rotate on all these three axes. Now the molecule, since it is spinning about its axis, it will resemble a spinning top, and hence it gets its name, the symmetric top molecule. Now, it is classified into two. These molecules are classified into two based on the value of IA. If IA is greater than IB and IC, they are called prolate symmetric top molecules. And examples are CH3Cl, CH3F, CH3Cn, and NH3. Whereas if IA is less than IB and IC, that is, if these bond lengths of hydrogen on either side, if it is less in BF3 molecules, this distance will be lesser. Hence, the moment of inertia there calculated will be less. So, the IA has values less than IB and IC. We get oblate symmetric top molecules. Examples are BF3 and BCl3. The next type of molecules are the asymmetric top molecules. Here all the principal moments of inertia are different. That is, IA is not equal to IB is not equal to IC. Examples are H2O molecule, then CH3OH molecule as shown here, and CH2OHCl molecule. Now let us understand the coupling mechanism or that produces the rotational spectra in these diatomic molecules. So assume an EM wave is interacting with a diatomic molecule. Now when this EM wave is interacting with a diatomic molecule, it exerts a force, a torque, a rotational force on this dipole. And this causes the molecule to rotate. Now, if the molecule is rotating along this axis of the bond length, it does not show any change in its dipole, right? That will not produce any dipole moment change, and it will not produce a rotational spectrum. But if the molecule is rotating along an axis passing through the screen, if it is rotating about that axis, this dipole will continuously change its position. It will rotate in this manner. So this positive center will become negative and this negative center will be positive. Again, it will change, alternate. That will produce a dipole moment change. And that produces a rotational spectrum. So when the dipole rotates about an axis perpendicular to the bond, the dipole moment varies periodically. And that variation is shown here. So the shift in this dipole moment, it will produce a fluctuating electric field. So this electric field then interacts with the incoming electric field of the electromagnetic wave. And this produces the rotational or microwave spectrum. So in this spectroscopy, we understand the spectrum from homonuclear diatomic atoms and heteronuclear diatomic atoms. So homonuclear diatomic atoms like the hydrogen molecule, oxygen molecule, nitrogen molecule and chlorine molecule, they have zero dipole moments since they are non-polar molecules. Hence, they do not have any change of dipole during rotations. So, no interactions are seen with radiation. Hence, we say homonuclear diatomic molecules are microwave inactive. They don't have any rotational spectra. Whereas heteronuclear diatomic molecules such as hydrogen chloride, hydrogen fluoride, and carbon monoxide, HCl, HF, and CO, they have permanent dipole moments since they are polar molecules. So they produce a change of dipole during the rotation and hence the interaction with radiation takes place. Therefore, we say heteronuclear diatomic molecules are microwave active. Now, let us understand the ideal case of rotation in a molecule, and for that, we take the case of a rigid rotator. Now, by a rigid rotator, we mean that two atoms of masses m1 and m2, they are connected by a rigid bond of length r0. So while the molecule is rotating, the bond length will not change. For the rigid bond, R0 is given as R1 plus R2, and for the rotation about the center of gravity Cm, we have the relation M1R1 is equal to M2R2, which is equal to M2 into R0 minus R1. That is, M1 plus M2 into R1 is equal to M2 R0. Now rearranging this equation, we can write R1 is equal to M2 R0 divided by M1 plus M2. And substituting for R1 in this earlier equation, we get R2 is equal to M1 R0 divided by M1 plus M2. Now the expression for moment of inertia about the center of mass, we have taken it as IC is equal to M1 R1 square plus M2 R2 square. Substituting for R1 and R2 values, we get M1 into M2 R0 by M1 plus M2 the whole square plus M2 into M1 R0 by M1 plus M2 the whole square. We have the common terms M1, M2 R0 square in the numerator. Taking it outside, we can write IC equals M1, M2 R0 square into M1 plus M2 divided by M1 plus M2 the whole square. Cancelling out the common terms, we get M1, M2 divided by M1 plus M2 into R0 square. Here, the masses can be reduced to another term mu, reduced mass mu. Hence, the expression becomes IC is equal to mu R0 square. Here we understand that the two-body problem is now reduced to a one-body problem. Now, when this rotator, this molecule is rotating, it cannot rotate in all possible values of angular moments. It will be discrete. So, the angular momentum of the rotator as L is equal to mu VR. So, instead of mVR, we have used the expression of reduced mass instead of m. We write L is equal to mu VR. Substituting for velocity in terms of r omega, we get mu r into r omega, that is mu r square omega. Mu r square is the moment of inertia of the molecule, hence we get L is equal to I omega. Now, according to the Bohr-Sommerfeld quantization rule, closed integral of angular momentum along all possible directions of rotation, it will be equal to integral values of Planck's constant. That means the integral value of angular momentum, it cannot have all possible values of energy. It cannot rotate in all possible values of energy. It can rotate only in particular specific possible values of energy, and that is given by NH. Since rotation is from 0 to 2 pi, we integrate from 0 to 2 pi angular momentum L, and we get L, if it is a constant, L into 2 pi. That is equal to NH. That means L is equal to NH by 2 pi. Now, representing H by 2 pi as H cut, I can write it as NH cut, where N is the quantum number having values 0, 1, 2, 3, etc. It is represented as the principal quantum number. Now, the allowed energy values are given as, from the expression En is equal to L square by 2I. Substituting for L, we get En is equal to N square H cut square by 2I. Here, En is the kinetic energy of the molecule since it is rotating. Now, in classical mechanics, we had reached the values of energy values as En is equal to N square H cut square by 2I. But in quantum mechanics, instead of the principal quantum number N, we use the orbital quantum number L. So substituting for L into L plus 1 instead of N, we get energy values EL is equal to L into L plus 1 H cut square by 2I, where orbital quantum number L can have values 0, 1, 2, 3, etc. Now let us look into the rotational spectrum of a rigid diatomic rotator. When the molecule is rotating, it can rotate with quantized energies. So the rotational energy is quantized. And by using the Schrodinger equation, the rotational energy levels allowed for this rigid diatomic molecule are given by EL is equal to L into L plus 1 H cut square by 2I. That was the relation. Now, instead of using the orbital quantum number, we have used the rotational quantum numbers here to represent the rotation of the molecule. So L is substituted as J here, and H cut is written by H by 2 pi. Substituting these values, we will arrive at the expression EJ is equal to H square by 8 pi square I into J plus 1 joules, where J can have values 0, 1, 2, 3, etc. Here J is the rotational quantum number, I is the moment of inertia mr square, Mu is the reduced mass, that is m1 m2 divided by m1 plus m2, and r is the internuclear distance. So the rotational energy levels for the rigid rotor is Ej equals h square by 8 pi square I into j plus 1 joules, where j is having values 0, 1, 2, 3, etc. In spectroscopy, energy is usually expressed in the wave number units for convenience. That is eta j. It is equal to 1 by lambda. So wave number is 1 by lambda. Now 1 by lambda is equal to nu by c. Now writing the Planck's constant on both numerator and denominator, we get h nu by hc. H nu is equal to energy of the rotating molecule Ej. So we get eta j to be equal to Ej by hc. Hence, eta j is equal to Ej by hc, that is equal to h by 8 pi square Ic into j plus 1 centimeter inverse. Unit of eta j is centimeter inverse. Here j can have values 0, 1, 2, 3, etc. Substituting for h by 8 pi square Ic as b, we get the expression eta j is equal to b into j plus 1 centimeter inverse. Here b is the rotational constant. It is given by h by 8 pi square Ic centimeter inverse, and I has the value m1 m2 divided by m1 plus m2 r naught square. Using the reduced mass expression, it is equal to mu r naught square. Now, the energy of the jth state, eta j, is thus b into j plus 1. The energy of the j plus 1th state will be obtained by substituting j plus 1 instead of j. So we get eta of j plus 1 is equal to b into j plus 1 into j plus 1 plus 1, that is b into j plus 1 into j plus 2. Now the energy of the ground state is obtained for j equals 0. So eta j equals 0 is equal to 0. And let us represent it as this level. So here when j equals 0, eta j is equal to 0. Now the energy of the first excited rotational energy level, that is for j equals 1, is eta j equals 1 is equal to, substituting for j equal 1, we get 2b. So for j equals 1, eta j is equal to 2b. Energy is higher, so we get a energy level higher than the ground state. Now the energy of the second excited rotational energy level, that is for j equals 2, we have eta j equals 2 equals b into 2 into 2 plus 1, that is 6b. So we get an energy level for j equals 2 at 6b eta j. It is higher than the first excited level. Then for the energy of the third excited rotational energy level, that is for j equals 3, eta j equals 3 is equal to 12b. And that is obtained in this energy level for j equals 3, eta j is equal to 12b. Now for the fourth excited rotational energy level, for j equals 4, we get eta j as 20b, and it will be located as such. So by calculating the energies of the different energy levels, we have got the energy level diagram for the rigid diatomic rotator. Now let us look into the different transitions. Now, when a molecule moves from one energy level to the other energy level, we find the energy difference, and that energy difference produces that particular spectrum. So the energy difference between two states, J and J plus 1 states, is delta of eta when J shifts from J to J plus 1. That is, it is the difference of eta J plus 1 minus eta J. Taking the difference, we get 2B into J plus 1. So this is the energy difference between two nearby energy levels. Now in rotational spectroscopy, it is said that the molecule cannot behave in its own. It has to follow certain rules, transition rules. And one of the rules is its selection rule, that is delta J. The change in the energy level can be only plus or minus 1. Plus 1 represents absorption, that is, the molecule is shifting from a lower energy level to the next higher energy level. And minus 1 represents emission, that is, the molecule is shifting from the higher level to the next lower level. Let us assume absorption first. So if the molecule is raised from J equals 0 to J1 state, the energy difference delta eta from 0 to 1 is equal to 2B. It is represented by this green arrow here. Now, if the molecule is raised from J equals 1 to J equals 2 state, the energy difference delta eta 1 to 2 is 4B. Again, if the molecule is raised from J equals 2 to J equals 3 state, the energy difference delta eta 2 to 3 is equal to 6B. Likewise, when it is raised from J equals 3 to J equals 4 state, the energy difference will be 8B. Now, if we plot the spectrum of these transitions, in the spectrum we get lines at 2B, 4B, 6B and 8B likewise. So, here we see that the allowed rotational energy levels of the rigid diatomic molecule is obtained as such, and the molecule can have transitions, energy differences of values 2B into J plus 1 centimeter inverse by following the selection rule delta J is equal to plus or minus 1. And we get the allowed transition between the energy levels of the diatomic molecule as such, and the spectrum is shown below. Here we have to note that delta J equals plus 1 represents absorption and delta J equals minus 1 represents emission. Now this is the spectrum of a diatomic rotator, the rotational spectrum of a rigid diatomic rotator, and we see that the spacing between each spectral line is 2B. It is constant. Even though its intensity is varying, the spacing between the spectral lines is constant. By using this feature, we are able to calculate the value of rotational constant B. And by calculating B, we understand a value of I from it, since B is inversely proportional to I by the relation H divided by 8 pi square IC. If we get B, we can calculate the value of I. And from the value of I, we can calculate the value of the reduced mass. Now, in other ways, if the mass of the molecule is known, by calculating the value of B from the spectrum, we can calculate the value of R. That is the length, bond length of the diatomic molecule. Now let us have an understanding of the value or the range of the rotational energy levels. So this diagram shows the energy spectrum, and when the molecule is excited, it may rotate, may vibrate, and it may have electronic energies. Outer valence electrons can shift. So all of these shows different spectrum. Now the rotational transitions, they fall within this range. Okay, so they have the lowest energies. Only if the molecule acquires higher energy does it start to vibrate and show the other vibrational energy levels. Now, one particular feature used in rotational spectra is the isotope effect to study the mass or the contribution of isotopes in molecules. Now, the spectrum here is an example of the isotope effect observed. And due to the presence of the isotopes, we have an additional peak in the spectrum. This peak represents the rotational spectra due to the additional isotope. So when an atom in a molecule is replaced by its isotope, their interbond distance, bond length does not change, but the mass of the nucleus changes. This will cause a change in the moment of inertia, I, because it is equal to mr square. Since m changes, it will change I. Now, since the rotational constant B is proportional to 1 by I, that is, B is inversely proportional to moment of inertia, there will also be a change in the rotational constant B. So, for the first molecule, let us take that the energy difference from a state J to J plus 1 is delta eta J is equals 2B into J plus 1, where B equals H divided by 8 pi square IC. For the second molecule, the energy change will be different because the rotational constant has changed due to the change in moment of inertia I. So, when moment of inertia has become I prime, the rotational constant has become B prime. Hence, the energy change from the J to J plus 1 state will be delta eta J prime. That is equal to 2B prime into J plus 1. Here B prime is equal to H divided by 8 pi square I prime C. Now the shift in the wave number or shift in the energy is calculated as the difference delta eta J minus delta eta J prime. That is equal to 2B into J plus 1 minus 2B prime into J plus 1. Rearranging, we get the expression 2J plus 1 into B minus B prime. Now taking B as a common factor outside, we get 2 into J plus 1 into B into 1 minus B prime by B. Now B prime by B is equal to I by I prime, since they are inversely proportional, and that is equal to mu by mu prime. Now substituting this in the expression, we get isotope shift, that is delta eta J minus delta eta J prime is equal to 2 into J plus 1 B into 1 minus mu by mu prime. So from the isotope shift, we are able to calculate the reduced masses of the actual molecule and its isotope. This shows the rotational spectra for carbon 12 oxide molecule and carbon 13 oxide molecule. So for the carbon 12 oxide molecule, we get the spectral lines in the black lines here. And in the carbon 13 oxide molecule, we see the spectral lines shown by the pink dotted lines. So we understand that since the energy levels are reduced due to higher mass, nuclear mass, the rotational spectral lines are shifted. Now, when the replaced atom has greater mass, the isotope shift is positive. That's all for today's session. Thank you.